So today we're going to be covering the spec point 3.3.15 on the AQA specification called nuclear magnetic resonance spectroscopy, or NMR spectroscopy. And I'm going to go through a bit of the theory. I'm going to go through a bit of the theory associated with the spectrum, alongside how you might interpret carbon-13 NMR spectrums, hydrogen NMR spectrums, and how you will use that to derive a structure if the exam questions ask you for that, because those are like the really complex questions that are often asked at the end of organic papers. I'm also going to go over like why we use TMS as a standard, a lot of the different rules that's associated with different spectroscopy as well. Okay, so just moving very swiftly on. How does NMR work? We're going to cover a bit of the theory. Just to really clarify, all of this on this slide is extra information. This is not on the spec, but I think it's really useful to understand because it helps you to conceptualize what we're looking for in the spectrum and why we are looking for specific things in the spectrum as well. So essentially, the background knowledge for this is that when you have a nucleus with an odd number of nucleons, and what we mean by nucleons are protons or neutrons, so if there's an odd number of this, then it creates a nuclear spin. So you can see it on this bit. There's this spin, right? It's spinning in lots and lots of different directions, and that's because of the magnetic field that's generated surrounding the nucleus, and this is a very weak magnetic field. Now, what we're looking at in NMR spectroscopy is how this weak magnetic field interacts when you place it in a large magnetic field. Essentially, what we're looking at here is the energy that's absorbed by the nuclei. Now, there are lots it can get more complicated than this. I'm just basically really simplifying this down into the kind of basics, because they're, as you can see in this image on the right, they're moving in either in the direction of the magnetic field or against the direction of the magnetic field. And so you're basically looking at how the nuclei, when it spins in a larger magnetic field, rotates differently to how it rotates in lots of different random directions against the magnetic field. And that's what NMR spectroscopy is looking at, like the difference in their rotation and the difference in the amount of energy that's absorbed, i.e. the radio waves, the magnetic waves, which are absorbed in this alternative versus without that larger magnetic field surrounding it. You will see why this is important, because when you're looking at NMR spectrums, you're looking at chemical shift. You're looking at how much energy is absorbed by each of the nuclei. And depending on the direction that it's rotating in, it's going to absorb different amounts of energy. And that's really important to understand moving forward. So there are two different types of NMR spectroscopy that we should know about. There's carbon-13 NMR and there's hydrogen NMR. Now you can see here that there's already a link here, because why are we not looking at carbon-12? Because carbon-12 has an even number of nucleons versus carbon-13, which has an odd number of nucleons. So the reason why we're looking at carbon-13 and hydrogen is because they have an odd number of nucleons, and therefore they are generating this weak magnetic field that I spoke to you about. It says, does the direction they spin help identify the different groups in the compound? So essentially, the direction that they spin in affects the energy within each of the nuclei, essentially, right? So if it's moving in the direction of the magnetic field, it has lower energy compared to if the nuclei are moving against the direction of the magnetic field. Because of this, there's a lot more steps to this, which we don't need to know for this specific specification. But if you do want more information, I can go into a bit more depth. If it's moving in the direction of the magnetic field, lower energy versus higher energy, as I said, against the direction of the magnetic field. And when it's placed within this larger external magnetic field, the electrons and the nuclei essentially absorb the energy to move up and down energy levels. The short answer to your question is yes, but there's a bit more information that we're going to go into, because the amount of energy that they absorb is also going to be affected by the atoms which are surrounding the nucleus as well. So there's a lot more that goes onto it, but essentially you are right there. So the next bit of the kind of theory behind it is, what solvents do we use in NMR? So there are two different types of solvents which we use. It's either tetrachloromethane, CCl4, or CdCl3. Now, the general reason why we use each of these solvents is because they don't have any hydrogen atoms, as you can see. So they don't produce any peaks in the hydrogen NMR spectrum. Why is that important? Because it means that we won't be kind of getting confused between the peaks that are generated from the actual compound versus the peaks which are generated by the solvent. These solvents are also inert meaning they're very unreactive. That's important because it means it doesn't actually react with any of the samples that we're testing. And it also only produces one peak on the carbon-13 spectrum, but this is a known position, so it can be ignored. So essentially, because it has one carbon atom, it doesn't really matter that much compared to if it had a hydrogen atom in it, essentially. Now, I've put in the second major bullet point. We use CCl4 for non-polar compounds and CDCl3 for polar compounds. Now, why do we do that? This is basically a bit of a cross overlap with the bonding topic, but it's because of the actual structure of each of the molecules. So if I quickly just draw CCl4, the 3D structure for this, you can see that this is a tetrahedral shape. And if I just draw the partial charges as well, because chlorine is more electronegative than carbon, it's going to have a partially negative charge. Now, this is a symmetrical molecule, right? Which means that even though there are these polar bonds, these dipoles, as you can see, the delta negative, delta positive charges will cancel out. And so this molecule is actually non-polar. And that's why we use it for non-polar samples, because like attracts like, right? The other molecule that we use is CDCl3. So if I draw this out, again, this chlorine is going to be partially negative, and then carbon and deuterium are partially positive. Deuterium, by the way, is just 2 hydrogen atoms because we don't want to use 1 hydrogen because that will basically cause a peak. So we use deuterium instead. And the reason why this is basically polar is because there's one deuterium molecule. That means that not all of the dipoles will basically cancel out. And so that's why we use this compound for polar organic substances as opposed to non-polar organic substances. That's basically an exam question they might ask just to test your knowledge on polarity. But this, as you can see, is a cross overlap with the bonding topic. Now, moving on to the next kind of spec point reference, which is what standard do we use for NMR? Now, just to clarify what we mean by a standard, basically, when we're looking at NMR spectrums, we always have to look at the chemical shift value. I'll go in and explain what chemical shift means in a bit, but we're looking at how the chemical shift value is relative to a baseline, right? And that's what we mean by standard. It's like a baseline, a set baseline, or a point of comparison, if that makes it easier to understand. And TMS is the point of comparison that we're looking at, essentially. And that's because TMS, as you can see here on the kind of partial displayed structural formula that I have, we have identical methyl groups. We've got 4 methyl groups surrounding the silicon atom. And these 4 methyl groups essentially make it really good for use as a standard because it means that it only produces 1 peak. And I've listed these as points down below. So just to kind of reiterate, we use this as a standard to calibrate the spectrum, and so it only produces 1 peak, and it produces a peak at the delta 0 parts per million value, and this means that all chemical shift values are recorded relative to this TMS peak. So that's one thing. I guess within chemistry, there are so many examples of this occurring, so you could start to be making synoptic links. So for example, when we're looking at relative atomic mass or relative molecular mass, we're comparing all of the different mass numbers, etc., relative to carbon-12, right? So carbon-12 is as close as possible to 12, so we use that as a standard, for example. Similarly here, we're using TMS as a standard. So hopefully that makes a bit more sense of why we're using TMS. But there are different properties of TMS that make it very useful as well. The first property is that there's only one absorption peak because 4 carbon atoms and the 12 hydrogen atoms are all in identical environments. The absorption peak is also much further away from all the other peaks, meaning, i.e., you basically don't get confused. You won't basically mistakenly reference one of the TMS peaks with this peaks from your sample. It's also non-toxic, it's inert, and it's volatile, meaning it has a low boiling point. Why is that important? It means that you can easily separate TMS from your organic sample if you want to, make sure that there's no contamination or anything like that's basically occurring. So that's basically a lot of the kind of theoretical knowledge behind it. And so now we're going to slowly start to move it on into interpretation. So before we do that, just the last kind of bit on chemical shift. So I mentioned this briefly earlier, but when we look at chemical shift, we're basically looking at how much the magnetic field has shifted away from that of TMS, essentially. How much energy that particular nuclei has absorbed, which makes it move further away from the TMS peak, which is at this peak, which is at 0 parts per million. So in all spectrums, you'll basically have a peak at 0 because that's your standard. So you're essentially looking at how, as I said, the magnetic field and the energy of each of the nuclei shifts away from the standard TMS peak. So with all of that in mind, let's move on to analyzing carbon-13 spectrums and then hydrogen spectrums as well. So firstly, to understand how to interpret carbon spectrums, we need to be able to work out what carbon environments are, right? So within carbon-13 NMR spectrums, there's one peak for each set of equivalent carbon atoms. And so what I essentially mean by that is there's one peak for each carbon environment. This is really critical to understand. You need to be able to identify each of the different carbon environments, because that will really help when it comes to interpreting spectrums. So that's what we're going to do now. I'm going to highlight the different carbon environments with different colors. Hopefully that'll be able to make it easier to visualize. And I'm also going to write them down. So let's look at the compound on the left. This compound is propanol. I'm going to first highlight the first carbon environment that we have here. This is a carbon environment because you're looking at not just the carbon atoms which are adjacent to the carbon that I've highlighted in yellow, but also the atoms surrounding it. So you can see here that there's different atoms attached to either side, and so that makes it a specific, a separate carbon environment. The next carbon environment is a central carbon environment over here, the central carbon, and the last carbon environment is this carbon environment. So you've got 3 carbon atoms, and each of these are in separate carbon environments because they're surrounded by separate atoms. So you can see here for this pink one, this pink one is surrounded by 3 hydrogen atoms on the left, and then this whole structure on the right. You don't just look at just the adjacent carbon, you look at everything surrounding it, and that will make it really helpful when you look at more complex structures as well. Just make sure you're able to visualize sort of all of the different molecules which are attached surrounding that carbon atom that you're looking at. So just to point this down, there's going to be 3 carbon environments here, meaning on the spectrum, there's going to be 3 peaks. The number of carbon environments are directly correlated essentially to the number of peaks that you have on a carbon-13 spectrum. Moving on to the next molecule, so you can see here that this molecule is written really wrong as well, actually. Okay, this is meant to be an ester. So this looks like it is ethyl ethanoate. And if I again write out the different carbon environments that you can see here, so you can see that there's one carbon environment here, there's another carbon environment here, here, and here. Because, a different color, because each of the different carbons are attached to a different series of atoms, as you can see. So with the blue one, it's attached to this kind of structure on the left, and then this kind of structure on the right. So if I just write this down, this one has 4 peaks because it has 4 carbon environments. Then finally, on the right, we have this molecule, which is ethanoic anhydride, right? And ethanoic anhydride, as you can see, if I try to highlight the carbon environments here, there's one here, but this carbon and this carbon are basically attached to the same atoms on either side. So you can see that there's oxygen, a methyl group on one side, and then there's this kind of structure on this side. And then are the 2 CH3s in the middle compound 2 different peaks because one of them is bonded to the CO and the other, yes, you're correct. Likewise, if I highlight these ones, this carbon and this carbon are also the same environments because you can see adjacent to them, but also surrounding those molecules, they're attached to exactly the same atoms at exactly the same distances as well. So that makes them the same environments. So that's basically going to be 2 peaks. Even though there are 4 carbon atoms, you can see here that there are 2 peaks. So you need to be really careful. Now, I'm going to move on to how you identify carbon environments from aromatic structures. And that's because it's a bit more difficult, but it does get easier when you work out certain tricks that you can use. So how I do this and how I make it easier for myself is by drawing a line of symmetry. Drawing a line of symmetry makes it so much nicer because then you can easily see which carbon environments seem to be identical to one another. So for the far left one, let's just get started with that. I'm going to draw a line of symmetry straight down the center, right? And then I'm going to highlight, just like I did before, the different carbon environments. So you can see here that using line of symmetry, I know that these two are the same carbon environments. These two are the same carbon environments. And these two are the same carbon environments. And so I know, therefore, that there's going to be 3 peaks because I've got 3 carbon environments. I hope that makes sense. Then, moving on to the next one, I'm going to pretend to draw a line of symmetry in the center, but you can see here that this is actually not a line of symmetry because you've got 2 different molecules. So you've got a methyl group on the right and then an NO2 group on the left. So you can't really draw a line of symmetry there, but you can still use that to help inform your understanding. So here, this is going to be 1 carbon environment, right? Because there's a CH3 and that's a carbon. Oh, sorry. Can you repeat that, please, for the first one? Okay, I can repeat that. That's okay. So just to clarify, I have a line of symmetry down the center, yeah, diagonally. And then in yellow, I've highlighted a carbon environment, right? These are both the same carbon environments because you can see here that this carbon is attached to an NO2 group, and so is this carbon on the same side. And then they're both attached to this same symmetrical bit of the hexagon, right? And so that means that they're the same carbon environments. Similarly, for the blue, the carbons which are highlighted in blue, they're also surrounded by the same molecule. So you can see here that this carbon is attached to a CH and then an NO2. So is this a CH and an NO2? And then it's also attached to the same molecules on this side as well. So it's the same environment. And then similarly for the pink, it's attached to this NO2 side and then also this molecule, which is exactly the same, which makes them the same carbon environments. Are there peaks for each pair of carbon atoms, or can there be a different number of carbon atoms in a set? From what I understand from your question, there's going to be 1 peak for each of those pairs, essentially. And there can be a different number of carbon atoms in a set. I think hydrogen NMR gives you a bit more information about that. Carbon NMR simply talks to you about how many different environments there are. It's not necessarily a pair. It doesn't have to be just a pair. You can have, if there are 3 carbon environments, which have maybe like 9 carbons, etc., you can have like, it will still be just 3 carbon environments, as long as you have the same number or the same number and type of atoms adjacent to the carbon is going to be the same environment. I hope that makes sense. Okay, so moving on to the second one, I hope that it made sense when I reiterated the explanation with the first one. But you can see here that the one I've highlighted in yellow, CH3, is going to be 1 carbon environment. Similarly, this one is going to be a separate carbon environment because it's attached to a carbon, and this one's attached to a CH3. And this whole molecule on this side, which is different. Then you have this one and this carbon, which are the same carbon environments. Why are they the same? Because they're both attached to a similar NO2, NO2 groups on this end, and then they're both attached to this side, which are exactly the same. So they're the same carbon environments. And then we've got these two, which are the same carbon environments, and this, let me use a different color, which is a different carbon environment. So you can see here that this is going to be 6 peaks because there are 6 different colors, i.e. 6 different carbon environments. I hope that makes sense. Basically, look at not just the adjacent carbon, but generally the carbons surrounding the carbon that you're looking at, essentially, to make sure that you correctly identify the different carbon environments. Looking on the far right, I'm going to draw a line of symmetry for this one as well, because you can, from the center here. And then I can use that to work out the different carbon environments. So I can see here that this carbon environment and this carbon environment are the same. This carbon environment is going to be different. This carbon environment and this carbon environment are the same. And this carbon environment is different. Because, as you can see, that this one's attached to an NO2, and then it's attached to a CH2, a CH, 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 and this one's attached to the same. It's attached to a C here, and then a CH2, CH2. It's attached to exactly the same number of carbon atoms on either end, so it makes it the same environment. That means that you have 4 peaks, because you've got 4 different colors here. Okay, why isn't the carbons on the line in the same environment? Okay, they're not the same environment because you can see here that this carbon that I've highlighted in yellow is attached to a CHNO2, a CHNO2, right? But this carbon environment on the far, like on the line of symmetry over here, is attached to a CH, CH, and then an NO2. A CH, a C, and then an NO2. A CH, a C, NO2. So they're not the same. They're not attached to the same number of carbon atoms on either end. Does that make sense? Like, it's not attached directly to the same number of carbon atoms. If the NO2 was on the carbon 4 instead, would the carbons then be in the same environment? So, if it was attached to the carbon 4, it would be in the same environment, exactly. Well done, yeah. Okay. Great. Right. So now moving on to how we're going to put this in a very simple kind of representation by a carbon shift. So this particular molecule that I'm representing here is actually ethanol. Right? So I'm going to quickly draw the structure out, and then hopefully we're able to use the figure here, table C, and the spectrum to work out exactly why we've got these peaks, these 2 peaks on the spectrum at the locations that we have them in. So I'm going to highlight these in 2 different colors. So we can see here that there's a peak at around 40 to 60 in this particular range, right? And I'm going to highlight that in blue. And then there's also a peak at around 20 parts per million, and I'm going to highlight that in pink. Now we can see here that there's 2 peaks, right? So there must be 2 carbon environments. So we're already using the knowledge that we've gained. There's 2 peaks and there must be 2 carbon environments. And if I've already told you that this is ethanol, meaning that you can see that there are 2 carbon environments. And what are the 2 carbon environments? There's a carbon environment here and there's a carbon environment here. We just need to work out what carbon environment we're referring to when we're looking at each of these peaks. Okay, so this is where the table comes in handy. So I've already mentioned that this peak around, the blue peak is around 60. And so knowing that the structure is ethanol, I can already distinguish that this peak seems to be around in this particular range, and therefore it seems that we're looking at CO, right? And then the pink peak is around 20, and so that seems that we're looking at around here, because again, as I said, it is ethanol, and so it can't be attached to a halo, like a halogen. It can't be attached to a C double bond O or anything like that. So we know that that therefore is going to be a C single bond C peak, and therefore I can highlight that therefore this peak, the blue peak, is referring to this carbon, and the pink peak is referring to this carbon. I hope that makes sense. Is the ethanol already given in the question? Yeah, this in this particular example, it was already given in the question. I'm just using it to help you illustrate the actual carbon spectrum itself, so you know how we're going to basically distinguish between each peak on the spectrum, if that makes sense. We're going to do other questions where we're deriving the structure ourselves, by the way, just to make sure. And if the ethanol wasn't given, can you assume it's propanol? You can't. And I can tell you why. You can't, because propanol, let me quickly draw this out. Propanol, without drawing the hydrogens, you can see that there are 3 carbon atoms, right? And each of these have different environments. This is going to be a different environment. This is going to be a different environment. This is going to be a different environment. So you would have 3 peaks if it was propanol. So you can't assume that it's going to be propanol. But that's a good question. You can't, because you have to basically, I think for carbon spectrums, the most important thing is looking at the different environments. Now, I want to give you a bit of an explanation why this is the case. Basically, the blue peak, you can see, is shifted further to the left, right, than the pink peak. You might be like, why? Why is it? And that's because of, as I said initially, it's basically because of the atoms which are surrounding the carbon environment and how that links to the energy that's absorbed by the magnetic fields. Yeah? So this oxygen atom that's attached to the carbon, right, means that the electrons which are surrounding this carbon, like imagine there's a lot of electrons here, are actually attracted towards the oxygen, right? Because oxygen is more electronegative. Because of that, that means that carbon is attached to fewer electrons than this carbon atom, right? Because this isn't attached to an electronegative atom, or is attached further away from oxygen. But this one is attached directly to oxygen. And so this means that because there's less electrons surrounding this carbon, it's going to absorb more of that energy, more of that radio waves, more of that magnetic fields within that kind of larger external magnetic field, as I mentioned. And that means that the shift is further to the left. It's absorbing more energy, and so the chemical shift is further away from the TMS peak, which would be at 0. Yeah? I hope that makes sense. You don't really need to know about that, but it's good to understand so that you don't even need to look at the chart to work out which peaks refer to which carbon, because you would have been able to do so by simply looking at how much further away it is from TMS peak. Yes, it's about electronegativity. Why does a lower number of electrons mean energy is absorbed more? It means that's a good question, and it's because of shielding. If there's less electrons that's surrounding the nucleus, then that means that there's less shielding. It's going to be directly, it's like, imagine there's like so much energy, there's nothing protecting it from the energy. And so if there's less electrons, it's going to absorb more energy. There's more electrons, it's going to absorb less energy because there's more shielding, there's more protection essentially from the energy. Yeah? Okay. Now we're going to do one where we're actually deriving the structure ourselves. So let's say that here we have the spectrum and we have 5 peaks, right? That's the first thing I'm going to look at because, as I said, peaks are often the most important. So 5 peaks meaning that there's 5 carbon environments. And you can see here that I've got the molecular formula where there's C5H10O2. Yes. Oxygen pulls the electrons away from carbon, so carbon has less electrons, so it absorbs more energy. Yeah, exactly. Because there's less shielding surrounding it. Could you say that a more polar an environment is, the further it is from TMS? The more polar, essentially, yeah, I would say. But you have to make sure that it's next to a more electronegative atom. So, yeah, that essentially also makes sense. So, looking back to the spectrum, you can see, as I mentioned, there's 5 peaks, there's 5 different carbon environments, and we've got this molecular formula of C5H10O2. Now, I'm going to start just quickly jotting down what I would do in an exam myself, which is basically looking at the different chemical shifts and the table and seeing what I can deduce from the structure. So I already know there's going to be 2 oxygens somewhere in the structure, so I do want something where there's 2 oxygens. But you can see here that this first peak is between this 160, 180 range, and so that's around here. This makes more sense, actually. So 160, 185. So this basically is an ester peak, right? So it's an RC. This peak is going to be there. So I'm basically just, it's a bit like working out a jigsaw puzzle or like a detective, being a detective, basically trying to figure out the structure by looking at little bits and pieces of the structure. So here we have this C-double-O carbonyl group. Then we've got this peak at 60 to 80 in this range. And so that seems like it's going to be this peak over here, because that basically occurs in the range. So CO, and I also know there has to be 2 oxygens, so I'm using that knowledge in this particular peak. And there's 2 peaks within this range. And so that's around in the 20 to 50 range maybe. So you can see there's something here. I'm just going to write the numbers here just because I don't have enough space. And then also this one here, these ones seem to be in the 5 to 40 range because this one's not directly at 20. Right, so now I've just kind of jotted down the different chemical shift values that I think each of the peaks might be. And now I'm going to try and use that to work out how I might look at the structure. Often in exam questions, there are a bit more guidance in a lot of these questions, but I'm just going to go in sort of trying to investigate how we can get 5 carbon atoms, 10 hydrogen atoms, and 2 oxygens through this. So I'm going to just start off with drawing the ester bond, right? So there's a C double bond O, and we can already see that there's an oxygen peak here as well. So I'm going to put one there. And then I'm just going to basically play around with the structure, because I know that there's a 20 to 50 peak here, which is just saying that there's a carbon attached to the C double bond O, and there's just carbon atoms next to each other. And so that doesn't give me much information. So that essentially means that I can just sort of try to work out a structure that will give me 5 peaks. So let's say I just put a carbon here, a carbon here, right? And so that gives me 3 hydrogens. And I'm going to put 2 hydrogen atoms there. So now let me just kind of cancel out the number of hydrogens I've used. So I got 3 hydrogens used up, so I've got 2 hydrogens left. I've used 5 hydrogen atoms, so I've got 5 hydrogen atoms left, and I've used up both of my oxygen. So this is basically an ethyl group. I can just add that here, and so that will give me my structure, right? So that's basically me just using what I know, that there's going to be this carbonyl group and this C single bond O group, and just putting them into a structure. And let me just count the number of environments. There's 1 environment here, 1 environment here, 1 environment there, 1 environment there, and 1 environment there. So there's 5 different environments, and each of them end up actually, they meet the criteria of the molecular formula, because we've got 10 hydrogen atoms, 5 carbon atoms, and 2 oxygen atoms. I guess you can also, just from looking at this now, you can also draw this differently. You can also draw this like this, because as you see, the spectrum doesn't give us information about the number of hydrogens or anything like that, but carbon spectrum does. But you can also draw this like this, where you put this carbon, where you can basically put this CH2 on this end, essentially, because again, both of them are basically attached to a C double bond O. And you can see that there's a 20 to 50 peak here, which means that regardless of whether it's a CH3 or a CH2, they'll both basically produce the same peak. So you can also have something like that. And again, these will also have 5 different carbon environments. So that also works. And you can see here that this basically shows us that a lot of the exam questions, they often accept more than one structure. You just have to make sure that they meet the different criteria you're looking for. Can you explain that again, please? How come you didn't use a carbon bonded to O on the 4th peak in the final structure? Okay, how come you didn't use the carbon bonded to O? Which carbon bonded to O? Is it the double bond O or the single bond O? I mean, it doesn't really matter which position you put the C double bond O in, the single bond O. So the reason why I didn't do it is because you can see here that if I did put it something like this and then something like that, right? I think that's what you're trying to say, like something like that without putting it in an ester linkage or something like that, is because if I did do like that, I would have to have 2 peaks which are in this 20 to 50 range, if that makes sense. Because that means that there will be 2 different carbon environments which are directly bonded to C double bond O, but I only have 1 peak in that range, and so that can't happen. If that makes sense. I hope that makes sense. I got 2-methylbutanoic acid. Okay, we can see if that works actually. So you got 2-methylbutanoic acid. Okay, so I can directly see here that there are 5 different carbon environments. Let me just count the hydrogens. Okay, there are also 10 hydrogens and 2 oxygens. Now we just need to make sure that they match the peaks. So there's a COH, okay, that makes sense. There's also a CH3, yep, 2 C's. Yeah, I think that works actually. That should work. Sorry. But yeah, the spectrum does show 5 carbon environments. It can't be 3-methylbutanoic acid, because that will mean that there are 4 carbon environments. Does that make sense? 2-methylbutanoic acid would work because there are 5 peaks in the spectrum. 5 carbon environments would work. No, there's 5. 1, 2, 3. There's 1 here. 4, 5. So I hope that makes sense for everyone. Can you please show where you got the 5 peaks from if you drew the pink structure? Okay. No, the small one isn't part of the bigger one here, by the way. But yeah, I can show where you get the 5 peaks from if you draw the pink structure. If I drew the pink structure, basically, I'm just saying that this peak, because these are both 5 to 40, right? They're both basically representing these C to C single bonds, right? So this means that basically it's this peak, this structure and this structure would have a very similar spectrum. It's just I'm exchanging the carbon here and here. Yeah, the splitting patterns are only in proton NMR, and I'll go through that in a moment. Okay, so let me quickly just move on to proton NMR. Proton NMR is just a bit more difficult, so that's why I want to spend a bit more time on that. So how I'm going to look at it is I'm going to look at it in 4 stages. We're going to look at peaks again, integration number, proton environment, splitting pattern. And I'm going to go through what each of these mean as well, hopefully. So, peaks. Now we're going to look at protons rather than the carbon atoms. And it's exactly the same process. We're looking at the protons which are adjacent to the environment you're looking at. So, the first proton environment you can see here are these 3 hydrogen atoms. These 3 hydrogens are attached to the same carbon, and they're also attached to the same adjacent atoms. You've got CH2 and you've got an OH that's attached to each of the hydrogens, which means that that's one peak. The other one, these 2 hydrogens, same environment, and this hydrogen is also the same environment, which means that you've got 3 peaks. I hope that makes sense. Moving on to this central one. So this central one is propanone, and propanone, you can see here, is actually all one hydrogen environment because it's a symmetrical molecule, and these hydrogen atoms are actually attached to the same adjacent carbon, the same adjacent C double bond O group, etc. So that means that it's exactly the same environment. So here you have 1 peak. And then the final structure, this is skeletal, so it's a bit more difficult to visualize, but hopefully we're able to do so. So you're going to have 1 environment, a CH3 group. And then in the middle, you're going to have this one, which is also a separate hydrogen environment. This one, the C double bond O, is attached to no hydrogen, so there's going to be no environment there anyway. There's going to be a hydrogen environment, a separate hydrogen environment here, here, and here. So these 3 are the same because they're both CH3 groups, CH3, 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 and they're all attached to exactly the same environments on either end. It's going to be attached, each of these CH3 groups are attached to a carbon, an oxygen, a carbon, an oxygen, a CH2, and a CH3 group, if that all makes sense. You're essentially just looking at the carbon atoms and the hydrogen atoms which are adjacent to the hydrogen you're looking at. Okay, next one is integration number. Now, integration number, relative peak ratio, integration ratio, they all mean the same thing. And what they're basically looking at is the number of hydrogen atoms which correspond to each peak. So it represents the number of hydrogen atoms, essentially, right? And this is what it actually looks at. You never need to have to calculate this, but it's useful to know. It's the area under each peak. And that's what we mean when we calculate the integration number or the relative peak ratio. So I've got exactly the same molecules as we looked at in the previous slide here. So I'm just going to do this so that you can see both the peaks and the integration number that we're going to calculate below. So I'm going to quickly highlight them again. So this one, it's basically you counting the number of hydrogen atoms. So this ratio is going to be 3 to 2 to 1 because you've got 3 hydrogen atoms in one peak, in one peak, and two hydrogen atoms in another peak, and 1 hydrogen atom in another peak, right? So that's going to be that ratio. The next one, this one, propanone, because these are all the same hydrogen atoms, you can write 6, but it's a ratio, so it's basically just going to be 1 because you don't have anything to compare to, so it'll just be 1 in this sense. And then, for the final one on the right, if I quickly highlight these again, this one is going to be a 3 to 2, because this is a CH3. The yellow is a CH3. This is a CH2 group. And this one is CH3, CH3, CH3. So how many hydrogen atoms is that? That's 3 times 3, which is 9. So that's going to be a 3 to 2 to 9 ratio. I hope that all makes sense. Yeah? Okay. So now we're going to, if that all makes sense, we're going to look at a spectrum now. I'm going to do this before looking at splitting patterns, and then I'm going to build it up on splitting patterns so that it's not so much information all in one go. So looking at this particular molecule here, so we've got methyl propanoate, right? I'm going to quickly highlight each of the different hydrogen environments. So these are hydrogen, this is one hydrogen environment, this is one hydrogen environment, and this is another hydrogen environment. And then I'm going to look at each of the different peaks. So you can see here that this peak on the far left seems to be in this 3 to 4 range. And so it refers to this 3.1 to 3.9. So that's going to be a ROCHHH peak. I'm going to just write the different integration ratios. This will be given to you in the exam question as well. So there's also, this is a CH3RO peak, just looking at the table. The second one you can see here is between like the 2 to 2.5 region. And so that basically seems to be in the 2.1 to 2.6 spectrum in chemical shift value. And so that's going to be RCOCH. And because it's 2, I know it's going to be like this, right? And there's going to be a carbon here or something like that because there's only 2 hydrogen atoms attached to it. And the final one seems to be in the 0.7 to 1.2 range. And so that's just going to be RCH3, right? So now you can see that all of this actually corresponds quite nicely to the highlighted structures I've drawn above. So this RCH3 refers to that. This HH refers to what I've highlighted there. And the pink refers to these 3 hydrogens. So that's basically how I'm using integration peak ratios and hydrogen environments to look at the spectrum. I hope that makes sense. I'm going to now move on to splitting patterns. Splitting patterns, basically what you need to understand here is the n+1 rule. You're looking at the carbon atom that's adjacent to the hydrogen atoms that you're looking at. So you look at the adjacent carbon, and then you're looking at the hydrogen atoms which are attached to that adjacent carbon. So if there are zero hydrogens attached to the adjacent carbon, it's going to be a singlet peak because it's the n+1 rule. So n basically refers to the number of hydrogens. So if there's 0 hydrogens, then it's going to be a singlet, one peak, one split peak essentially. If there are 1 hydrogen atom attached to the adjacent carbon, it's going to be a doublet. And then if it has 2 hydrogen atoms attached to the adjacent carbon, it's going to be a triplet. If there are 3 hydrogens attached to the adjacent carbon, it's going to be a quartet peak, right? Because you're following the n+1 rule. 3 plus 1 is 4, so it's going to be split into 4 separate peaks. You just have to look at the adjacent carbons essentially, and then see the number of hydrogen atoms attached to it. And this gives us basically, it's a bit more descriptive. It allows you to basically work out a bit more information about the structure. So I'm going to give you a little example here. So there's A, B, and C, and we're going to work out what each of these peaks are going to be, linking to the splitting pattern. So you can see that they're obviously, because of A, B, and C, you have 3 in separate hydrogen environments. And then there are 3 different hydrogen environments, and I'm now going to work out the splitting pattern for each of them. So A. Now A, this carbon atom A, is attached to an adjacent carbon that's attached to 2 hydrogen atoms, right? I hope everyone can see that. So the adjacent carbon here is attached to 2 hydrogen atoms. So what do we see? If it's attached to 2, 2 plus 1 is 3, so it's going to be a triplet peak, right? Because adjacent carbon has 2 hydrogen atoms. Now looking at B. B is attached to the adjacent carbon here is attached to 3 hydrogens, If it has 3 hydrogens, 3 plus 1 is 4, it's going to be a quartet peak. This one, you might be wondering, why don't we look at this carbon and be a singlet because there's no hydrogen atoms? You basically look at both and you add them together. So you look at here, there's 3 hydrogens, so we're going to be 3 plus 1 is 4. But here, there's no hydrogen, so it doesn't actually matter if you look in that direction or not. And for the last one, you've got the CH3 peak. And this is attached to an adjacent carbon. This is attached to an oxygen, essentially. But that oxygen is attached to... Okay, thought it would drop out. That oxygen is basically attached to no hydrogen, so that basically is just going to be also a singlet peak because it's attached to no hydrogen atoms. Splitting patterns basically allow you to get a much better detailed description of the structure of a specific organic molecule, but they do make it a bit more complicated. However, it does come with practice. So with this particular question, with the integration number, always be labeled on the peaks. Most of the time they will be labeled on the peaks, yeah. So knowing that, let me just add this in actually. So that's 2, 3, and 3. Even if it isn't labeled on the peak, sometimes you can basically work them out as well. So for example, for the one I just labeled 2, actually we'll go in order. So you can see here that, let me just look at each of the different carbon environments. So there's hydrogen environments. This is one hydrogen environment, and then hydrogen environment. So you can see here that this is ethyl ethanoate, 3 hydrogen environments. And this peak on the far left that's shifted the most from TMS is in the kind of this region, right? And if I look on the table B, that's around here. There's 3.7 to 4.1. So if the question basically does give you the structure, then you know it's in this region of 3.7 to 4.1, where you're looking at the hydrogen that's attached to the oxygen on this structure, then you know that it has to be it has to have 2 hydrogen atoms attached to it, because there's only 2 attached to this pink color, right? So that's a way they might ask you to work out the integration ratio yourself. But if they do ask you to work out the integration ratio, they should give you the structure of the compound. Then you basically have the next peak over here, which is around 2 in that particular region of the spectrum. So that's, if I look at the picture, if I look at the figure, you can see that that's around 2.1 to 2.6. So let me just write that out. That looks like it's around 2.1 to 2.6, and so it's going to be RC-CHHH. Okay, I'm going to have to try to hurry up a bit because we've got 4 minutes left of this meeting before it cuts on me. I'm sorry for that, but that's just going to be attached to 3 hydrogen atoms, and then the last one, you can see here that it's around the 0.7 to 1.2 spectrum. This is going to be RCH3. Which is going to be referring to that peak. Now, we can also see the splitting pattern. So this is a quartet peak, and we can see why this is a quartet, because the adjacent carbon here is attached to 3 hydrogen atoms. 3 plus 1 is 4, and so it's a quartet peak. Why is this a singlet? This peak is a singlet peak because this carbon is attached to adjacent carbon, which has 0 hydrogen atoms. 0 plus 1 is 1, so it's a singlet peak. How do you know to label the peaks 2 to 3 to 3? I did that knowing the structure already. Often, again, as I said, questions often give you the integration ratio. If they don't give you the integration ratio, you can look at the actual chemical shift values and then work out what hydrogen environment is referring to and use that to work out the integration ratio. So I know that this one is referring to this hydrogen environment. There are 3 hydrogen atoms, and so it must be a 3, if that makes sense. And then you look at the last one, which is a triplet peak. Why is it triplet peak? Because it's attached to a adjacent carbon, which has 2 hydrogen atoms, and therefore 2 plus 1 is 3, and therefore it's a 3. Triplet peak. Now, this is the last question I want to go through with all of you, just because it's a pretty difficult question. So this question is pretty hefty, but I'm going to try and go through this looking at everything we've covered so far. So peaks, kind of using the framework. So peaks and then integration ratio, looking at the proton environment, and then finally the splitting pattern. We'll first look at the peaks. I also want to draw your attention to the molecular formula on the right, because you can see here that this is C7H12O3. And so that basically tells us that we need to have seven carbon atoms, 12 hydrogen atoms, and 3 oxygen atoms in our structure. So you can see here that there are 5 different hydrogen environments on either side. Okay, there are 5 different hydrogen environments, and so we've got 5 different peaks. The exam question basically gives you the integration ratio, as I mentioned before, and it also tells you the splitting patterns. You can see here that this table is really helpful, because when you look at simply the spectrum, it looks like that there's 4 peaks, because you can see that this particular area, it seems like they're kind of clustered together. So I'm going to use both of them to help me deduce the structure. Okay, so the first thing I'm going to look at, now that I know about the different peaks, knowing that there's 5 different hydrogen environments, is I'm going to actually look at the splitting pattern and the integration ratio together. So you can see here that the integration ratio for the peak at 4.10, which also refers to this peak here because it's on the far left, is a quartet peak. And this is basically a trick that you can use in a lot of exam questions. When it's basically a quartet peak, you can use that to work out what type of structure, type of group it might be attached to. It's basically you sort of making inferences along the way. If it's a quartet peak, we know that according to the n+1 rule, the number of hydrogen atoms must be 3. So it must be like a CH3. I'm just going to write these down. Obviously, I don't know what the structure is right now. I'm just basically doing guesswork to help me get to the final structure. I hope that makes sense how I got CH3 from quartet. If it's quartet, it's attached to, the adjacent carbon is attached to 3 hydrogen atoms, meaning that seems to be like a CH3 structure. Similarly, if it's a triplet, then I'm thinking CH2. Some CH2. Singlets are much more difficult because I don't know if it's a C double bond O, if it's a C single bond O, I don't know. So let me just not do anything there. And this triplet is, again, might be a CH2 peak. So this is me just basically hypothesizing here. Now I'm actually going to look at the different proton environments. So 4.10, what might that be referring to? I'm going to look back at table B, which you're going to be given on the data sheet. And I'm going to basically think about looking at, again, at the molecular formula, what it might be referring to. So this basically looks, it can't be this. It can't be RCH2Cl. How do I know that? Because there's no chlorine, there's no bromine in our molecular formula. And so it makes more sense for it to therefore would be 3.7 to 4.1, right? And therefore it looks like this particular peak is referring to the RCOO structure. Now I'm going to start drawing out the number of hydrogen atoms, because this, again, the integration ratio says there's 2 hydrogen atoms attached to it. So I'm going to draw the 2 hydrogen atoms attached to it. So basically, I'm breaking down the larger molecule into smaller molecules so that I can then put it all together to form the final structure. So there's 2 hydrogen atoms, and I've already kind of, as you can see in pink, I've already kind of hypothesized, oh, this might be next for CH3. So I'm going to write that down as well. So this is ACH3. And that basically means that I'm actually meeting the criteria of not just chemical shift value, but also the integration ratio, because there are 2 hydrogen atoms here, as we can see according to the integration ratio, and the splitting pattern, because I've got a CH3 next to it. You can see how I'm breaking the question down. Make sure you do that in questions, because often these questions are 7 marks, 6 marks, and they just throw it at you. So you have to make sure that you break it down to work out the larger molecule and you don't get it wrong. And now I'm going to move on to the next peak, which is 2.60. Looking at 2.60, that looks like it might be this peak over here, the 2.1 to 2.6 structure. Let me just write this out smaller. So this is a 2.1 to 2.6. So I'm going to just kind of write that down over here. So that looks like. And you can see here that this is a CH2 because there are two hydrogen atoms and as part of the integration ratio. And the splitting pattern is a triplet, meaning that the adjacent carbon must also be attached to two hydrogen atoms, right? And so I'm just going to do that. That's what I'm going to do for that one. And there's another one which is within this region. I can't distinguish it because of how the spectrum's been drawn out, but I'm just going to draw an arrow to it right there as well. And so that arrow seems to be like it's attached to, again, it's within the same region. There are just two peaks within that region. So it's again going to be an R. RCO. But you can see here that it's attached to a CH2 as well. I think if I drew it out, it's just going to look exactly the same, which is why I decided not to. But just for the sake of making sure that I do for every peak, it's going to be exactly the same because you can see here that it's attached to two CH2 and then it's a triplet again, so it's CH2. It's referring to exactly the same structure. And then I'm going to look at the next molecule, the next peak, sorry, which is 2.19. And the 2.19 peak, again, seems like it's referring to the exact same chemical shift value, right? So it's going to be RCO. But you can see here that unlike the others, which is attached to two hydrogen atoms, this is attached to three. So it's just going to be CH3. And this also makes sense because it's a singlet, meaning that the adjacent carbon you can see here is attached to no hydrogens. It can't be because carbon can only form 4 bonds. And so that means that it must be just that. That it seems to be like it's an end molecule as well. So see, I'm just looking at how I might work out the structure simply from each of the different components. And then finally, the last and final peak is at 1.26. 1.26 seems to be referring to a peak at around 0.7 to 1.2. Even though it is greater than 1.26, often you have to sort of look at what the diagram is referring to and also a bit of your own knowledge when you're looking at the chemical shift values, because the chemical shift values, unfortunately, they're not always very specific. They're not exactly right. They're just referring to the general area in which a peak might be located in. So I know that there's 3 hydrogen atoms attached to it, so I can just draw that out. And it's also attached to a CH2 peak. So I can draw that out. Why? Because as I mentioned before, from my guesswork, just from the beginning, it's going to be it's a triplet peak, so it might be attached to a CH2. So you can see here that I've got a lot of different tiny structures going all around the place. And now I'm going to use all of that to try to work out the final structure, which has a molecular formula of C7H12O3. To do that, I'm going to make these all kind of smaller, so I've got a bit more space to work with. So I'm going to draw it all over here on this side. I'm going to start off with this ester bond over here because I think it gives me a bit, like the most amount of like things that I've drawn out so far. So I'm just going to draw that out here. So I've got a C double bond O, CH2, CH3. So I've already kind of used up, basically, always look back at the molecular formula when you're drawing this as well. So I've already used up 3 hydrogen atoms. I've used 3 carbon atoms, 2 oxygens. So I just need 1 more oxygen. And also, I've used up 5 hydrogen atoms so far. So I need 4 more carbons, 4 more carbons, and I need 1 more oxygen. Then I need to basically look. So I've basically cancelled this one out. I've worked through this peak, the 4.10 peak. The next peak I'm looking at is this peak, these 2 peaks. They're both referring to the same thing. So they're basically both one and the same. And so I'm going to see how I might put this into the red structure. So if I draw it out like this, let's say, where I put the 2 CH2 groups and then C double bond O over here, And I'm doing that because I know that the C double bond O, again, as I said, is a triplet peak, so it has to be attached to two hydrogen atoms. The adjacent carbon has to be attached to two hydrogen atoms, but also because I know that this is a singlet peak, right? This will be this because there's no hydrogen atoms attached to it. This will basically not have an impact on the splitting pattern, meaning that for this peak, as we mentioned here, it has to be attached to a C double bond O, or else you won't basically be able, or the splitting patterns essentially won't make sense, which is why I'm arranging it like this. But again, I'll basically do a lot of trial and error if I don't get the structure right instantly. So I'm just going to draw it out like that, and then I'm going to use this structure because you can see here that I've already drawn out a structure that like this, where there's a CH3 at the far end. So now I'm just going to draw that bit out over here. And now I'm going to look at how many carbon atoms I've done. I've done 5, 6, 7. It's already set. Okay, I've got 7 carbon atoms. I've got 12 hydrogens, and I also have 3 oxygens. So you can see here that I've got the exact same molecular formula, and I've also, I think, met the criteria for each of the different splitting patterns as well. Because here we've got the CH3 C double bond O group over there. We've got the CH2 CH3 group on this end, as you can see here. This and this makes sense. We've got the CH2 CH2 C double bond O here, and then we also have the CH3 over there. Does that make sense for everyone, how I've arranged that molecule? Yep, okay. Essentially what I did, if that makes sense, is I've basically broken down each of the separate splitting patterns, separate integration ratios into each of their constituent molecules, and then I've used all of what I've learned to put together the overall molecule. Yep. Thank you so much.